check this out. We've got something really fun today. This is so amazing. Oh man, again?
11.1 and 11.2, Counting Methods, Part 2. We're going to look at questions that involve multi-step labeling. That would be if there's two groups that we have to choose from and treat them differently. Then we have to calculate the number of ways separately and then use the fundamental counting principle to combine them. Part A here is a review of what we've already done. There is a group of 7 students and 3 teachers vying for a position in a 5-act talent show. How many ways can the 5 acts be chosen? So we have a total of 10 people, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're going to choose 5 of them to be in the talent show, so we'll call them T for talented, and the other 5 we'll call them U for untalented. And now the question is, how many ways can we rearrange these letters? So we have 10 letters total, so to rearrange 10 letters is 10 factorial. Now we need to divide by the number of ways we rearrange these identical letters. So 5 factorial and 5 factorial, because there's 5 T's and 5 U's. And we can calculate this out. It's 252. Now the next part is multi-step. How many ways can the acts be chosen if we want 3 student acts and 2 teacher acts? So if we want 3 student acts specifically, then we're going to treat the student group and the teacher group differently here. So we have 7 students, 1, 2, 3, 4, 5, 6, 7, but we only want 3 of them, so we'll call 3 of them T's, and the other 4 we'll call U's. For the teacher group, there's only 3 teachers, 1, 2, 3, and we're going to take 2 of them, 1, 2, and 1 of them will be left out. Now let's treat these 2 groups separately. So for the first group, we've got 7, so we would have 7 factorial, and then we'd have 3 T's and 4 U's. For the teacher group, we'd have 3 total, and then we'd have 2 T's, and we'd have 1 U. We can put it there if we want, but it wouldn't change our answer. Now we're going to use the fundamental counting principle to multiply these together and combine them. So the first one is 35, and the second one is 3. So we get a total of 105 ways. And last, how many ways can the acts be chosen if they must all be students? Now we go back to the first way. We've got 7 students, 1, 2, 3, 4, 5, 6, 7. We want 5 talented students, 1, 2, 3, 4, 5, and 2 of them are not going to participate. Now, this is just one group, so we're going to have 7 total, and 5 we're taking, and 2 we're not taking. And this turns out to be just 21 ways. There are 7 men and 6 women working in an office. How many ways are there to make a committee of 5 if gender is irrelevant, as it should be in most cases? We've got 13 people here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. We're going to want 5 of them, 1, 2, 3, 4, 5, to be on the committee. And the other 8 we will be left out. 1, 2, 3, 4, 5, 6, 7, 8. Now, how many ways to rearrange those letters? Now, if you're tired of drawing this out, it might be easier just to think of this in your head. So we have a total of 13. So it's going to be 13 factorial in the numerator. And then in the denominator, we want 5 for the committee. So 5 C's when we draw it out. And we're not going to want 8, so 8 L's. And we can get that this is 1,287. Now, what if the committee must all be men? Well, you might think this is sexist, but maybe it's a committee about how to keep the men's washroom clean. So we have 7 men, and we're going to want 5 of them on the committee, and we're going to leave 2 of them out, and that will give us 21 ways to do that. Now the last one, we're going to treat the men and the women different. So to be politically correct, we must have 2 men and 3 women. So for the men, we've got 7 of them, and we're going to want 2 of them on our committee, and we're going to leave out 5 of them. Now for the women, we are going to have 6 of them to choose from, and we want 3, and we don't want 3. And we calculate these numbers separately and multiply them because that's the fundamental counting principle. So this is 21 times 20, and that equals 420 ways to make the committee with these requirements. There are 20 Canadians, 10 Germans, and 10 Japanese. 14 are needed for a world-saving team. How many ways can this be done if nationality is irrelevant? Now, I don't want to draw this out because drawing 40 dashes and 40 different letters is going to be kind of a painful experience. So I'm just going to do this without drawing it. We've got 40 people, and we want 14 of them. And that means that we're not going to use 26 of them. Now this is a pretty big number, but if we put in our calculator, we see that it is 23,206,929,840. All right, what if the team must be all Canadian? So there's 20 Canadians to choose from. We want 14 of them, and that means we don't want 6 of them. Put this in our calculator, a much smaller number, 38,760. What if the team must have 5 Canadians, 5 Germans, and 4 Japanese? Now, we got to treat these groups separately because we want to choose the Canadians from the Canadian group, the Germans from the German group, and the Japanese from the Japanese group. So the Canadians, there's 20 Canadians, and I want 5 of them. That means I'm going to leave out 15. And then, using the fundamental counting principle, I'm multiplying that with the number of Germans. That would be 10 factorial, 10 Germans. We want 5 of them, and we don't want 5 of them. And then the Japanese, there's 10 of them as well, and I want 4 of them, and I'm going to leave out 6 of them. And I multiply all that together, and I get 820,471,680. What about if nationality is irrelevant, but Mr. Little, me, a Canadian, must be on the team? So I'm taking up a spot. I mean, it was my idea. I'm putting myself on there. So now there's only 39 people left to choose from. And on the team, there's only 13 positions left for the team. And we're still leaving out 26 of them though. So I've taken myself out of this group and this group. And we get that this is 8,122,425,444. How many ways are there to rearrange the letters in Canada? So we have 6 letters, and there's 1 C, there's 1 N and D, but there's 3 A's. So we'll divide by 3 factorial. That gives us 120 ways to arrange those letters. But what if we wanted the N to come first? So 1, 2, 3, 4, 5, 6. We've got the N. It needs to come first. That means the rest of the letters are going to be shuffled around in these last 5 positions. So we've got a C, we've got an A, we've got another A, and a D, and an A. So only shuffling these ones, that means that we're going to use 5 of them, and 3 A's are identical, so we'll divide by 3 factorial. And that gives us much less. It's only 20 ways to do that. What if the letter N must come first? 1, 2, 3, 4, 5, 6. And the C must come last. So those are now locked in position and they're not moving. So the remaining letters are A and another A and a D and an A. And we're only shuffling those 4 remaining letters around. That means that 4 factorial, because we have a total of 4 letters, and there's 3 A's, so we're going to divide by 3 factorial. And this is just 4 ways to do that. 5 friends, Abu Albert, Bobvinder, Cathy, Dandeep and Evan Li, are posing for a grad selfie. How many ways can the friends line up if 2 of the friends, Dandeep and Evan Li, must be beside each other? So we've got Abu Albert, we've got Bobvinder, we've got Cathy, Dandeep, and Evan Li. And these guys want to be beside each other, and everybody else can just line up however they want. Now, if you think of this, we've got 4 things that are moving around. We've got Abu Albert, we've got Bobvinder, and we've got Cathy. And we've got these 2 friends that are going to move around. They could be at the front of the line, or in between, or at the end. So really, we're just rearranging 4 items. So that would be 4 factorial. They're all different, so no dividing by here. Now, for every arrangement we can make with these 4 overall items, Dandeep and Evan Li can switch places. So how many ways to rearrange these 2 guys? Well, that would be 2 factorial, or just 2. So we got 4 factorial times 2 factorial, and that's 48 ways for these friends to line up. Now, what if Abu Albert and Bobvinder will not be beside each other because they got beef? So we could think of all the possibilities. So I'll call this the long way to solve. Okay, so we got 1, 2, 3, 4, 5. So Abu Albert and Bobvinder could be like that, because then there's a space in between. They could be like that, and then there's 2 spaces in between. 1, 2, 3, 4, 5. And then they could be like that, so there's 3 spaces in between. Okay, now what if Abu Albert went in the second position? 1, 2, 3, 4, 5. That means that Bobvinder couldn't fit here or here. So he's got to go here, or he's got to go here at the end. Abu Albert can also go in the middle, and Bobvinder then would fit at the end. And he could fit here too, but I'm seeing a pattern here. If I put him in the front, it's like this one, but with them switched around. And then if I put Abu Albert here, then Bobvinder would be this one, or this one. And then if I put Abu Albert at the end, I'm just redoing all of this. So I'm going to just take all of these and multiply them by 2, and that will be them switching. So far there's 6 total ways times 2, because each one of these they could switch places. And then the other 3 people are going to be moved around in the remaining 3 positions. So that would be 3 factorial. Now that's 12 times 6 is 72 ways. Now this is the long way to solve. It's very confusing. What if you repeat or miss a possibility here? So this is probably not the way we want to do it. Let's look at everybody together. How many ways to rearrange all 5 people? That would be just 5 factorial. What if we subtracted off the ways that these guys would be next to each other? That's actually the answer from part A. There's 48 ways for 2 people to always be next to each other in a lineup of 5. So we can just subtract that 48 and also get the answer. And this is a lot easier than trying to do it this way. So again, this is the total number of ways to arrange 5 people in a line. We're going to subtract the number of ways that 2 people will be together, leaving the number of ways that 2 people won't be together. How many ways to arrange the letters in the word noise if the vowels must be together, but in any order? So here's a similar type question to the last one. We've got the vowels here that are going to move around like best buddies, and the N and the S are just going to move around by themselves. That means that we have 3 overall things that are moving around in this arrangement, so 3 factorial. And this would be, I'll just make a note, overall items moving. Okay, now how many ways to rearrange the vowels within those arrangements? So there's 3 vowels, so 3 factorial. So this would be for the vowels. So 3 factorial times 3 factorial gives us 36 ways. Now that we know how to calculate the answers to all these counting method questions, we're going to differentiate 2 types of questions. The first being permutations. That's when we're making an arrangement and the order or the position matters. Just like this question here, how many ways can 4 people line up for a picture out of a group of 7 people? So normally we would do 1, 2, 3, 4, 5, 6, 7 lines. 4 people are going to line up, and their positions matter. There's a first person, there's a second person, there's a third person, and there's a fourth person. And if the first and second persons switched spots, we would notice. It'd be a different arrangement. Now, 3 people are left out, and they're just grouped to the side, so their arrangement doesn't matter, but these guys do matter. So we would say that there's 7 factorial ways to rearrange 7 people, and 3 people here, their order doesn't matter, so it's 3 factorial. And we can get the answer, just it's 840 ways to do that. But since this happens so often, we have a shortcut formula for this. And we write it like this. It's N for total number of items, and then capital P for permutation. And some people remember permutation because it starts with P, and so does picky. Picky starts with P. We're being very picky because the position is very specific and it matters. Okay, so P for permutation, and then R is the number of items we're going to use in our arrangement. And the formula looks like this. So n factorial would be our 7 factorial. Okay, so in this question, we would say 7p4. And you can see that it's the same as what we were doing before. So 7 factorial, and then in the denominator, 7 minus 4 factorial, which gives us our 3 factorial here. Now, we don't want to put this in our calculator. We have to go to the menu twice to get factorials. And if we use this shortcut, we only have to go to our menu once to get this symbol. So it saves us a bit of time. So on a TI or TI 83 or 84, it's under math and then probability, and it's number 2. So an 83, it'll just take whatever number you have before. And on an 84, a newer operating system, it gives you a little box to fill in, so it looks much like this. So we can just put 7p4 into our calculator, and we'll get the same thing as we did before. Let's practice using this shortcut formula. There are 10 empty seats on a bus, and 6 passengers get on the bus. How many ways can they be seated? So this is a permutation because the order that they're seated on the bus matters. If 2 people switch seats, we'd notice. So we would have 10 empty seats. So that's our total. And we're making a permutation, or filling them, with 6 passengers. We can put this in our calculator, and we get 151,200. Next one, 15 horses run a race. How many ways can they come in first, second, and third? So we've got a total of 15. We're making a permutation because we have specific positions, and if a horse got first or second, we would notice the difference. So we're making a permutation with 3 of them. And we can put this in our calculator, and we would get 2,730. We have 20 posters made by students, and we want to hang up 7 of them in a line on the wall. How many ways can we arrange the posters? So again, this is a permutation because the posters are presumably different. Hopefully nobody copied each other and got the same poster. So we have 20, and we're going to line up 7 of them. And this would equal 390,700,800. The next one, 10 people are being considered for placement in a special baking club. There will be a president, a vice president, a treasurer, and 3 chefs. How many ways can these positions be filled? So for this one, it is a permutation because we have specific positions here, but then this 3 chefs ruins it all. So 10 people, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A president, fine. Vice president, treasurer, 3 chefs. And then we're going to have 4 people who are just the lowly cooks, or maybe they clean up after. So this ruins it. We can't use our shortcut formula. So for this question, we actually have to drop back to the way we were doing it before, 10 factorial divided by 3 factorial for the 3 C's, and 4 factorial for the 4 people that are cleaning up. Now, there could be other formulas we can use for this, but we're just learning this one shortcut formula for permutations. So when we get a question like this, we've got to revert back to the original way we were doing these questions. And that's why we started doing them this way, so you'd never struggle or get stuck when confronted with this question. The second type of question we're going to be looking at are called combinations. That's when we're grouping items and there's no position or order within the group. It'd be like this example here. We've got 4 students will get to go to Tim Hortons out of a group of 14 eager volunteers. How many ways can these students be chosen? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we'll call 4 of them T's for Tim Hortons, and we'll call 10 of them L's for left out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we could find the answer to this using our regular method, 14 total factorial, divided by 4 factorial and 10 factorial. And this actually equals 1,001. Now there's a shortcut for combinations as well because they occur so often. And this is going to be NCR. N is the total, so in this case 14. And R is the number that we're going to use in our group. So in this case, 4. And you can see this will work out to be the same thing. This is the N here is the N here. So this is 14 factorial divided by R factorial. So that would be this right here is R. And then we've got N minus R. So that would be 14 minus 4 factorial. And you can see that this is the same as this. And we can shortcut it by putting this into our calculator instead. On a TI 8384, it's under math probability number 3 instead. So we can type this 14C4 in our calculator, and we can get 1,001 without going and getting 3 separate factorial symbols from our menu. Let's practice this with this example. There are 12 females and 18 males in a bowling group. How many ways can a group of 5 be chosen to represent the group if gender is irrelevant? So first of all, we would have 30 people to choose from. This is a combination because once you're in the group, you're in. There's no specific roles mentioned. And we want 5 to be in the group. So this would be 142,506. What if there needs to be 3 females and 2 males? Now we're doing 2 separate groups here, so we're going to have 2 separate combination formulas. So 12 females, and we want to choose 3 of them. Then using the fundamental counting principle, if there's this many ways to choose the females and this many ways to choose the males, there's 18 choose 2, then there's this many ways total. So this would be 33,660. And there must be 3 females and 2 males, but Mohsen, one of the male students, must be on the team. He's taking up a position there. That means that we still have 12 females and we're still choosing 3 of them. But our males, we've assured that this guy is already on the team, so that only leaves us 17 to choose from. And since he's taking up one of these spots here, we only want 1 more. So that would only be 3,740. How many ways are there to rearrange these beautiful cars if the red ones must all be beside each other? So these guys are like buddies that are inseparable, so they'll move around like a group. So in total we have 1, 2, 3, 4, 5, 6 items moving around overall. And for every one of those arrangements, these 3 red cars, they are different, so they are identifiable. They can switch positions. So how many ways to rearrange these 3? That could be 3 factorial. Now that's 4,320, and that was a pretty easy way to do this one, but we could use permutations for this. There are 6 items here, and we're making a lineup or a permutation with all 6 of them. And for this group, there are 3 of them, and we're going to make a permutation or a lineup with 3 of them. And if you do it that way, you still get the same answer, of course. This was part of permutations and combinations 1, 2, and 3. So hopefully you can use the combination and permutations formulas and do a multi-step question. Here are some questions from the textbook. Give them a try, see if you know what you're doing.